We are looking at some more examples of using the disk method to find a solid. So recall the disk method is that if I want to find the volume of a function rotated about an axis, it will be the integral from a to b of pi times the function squared dx. And this is when we're rotating about the x-axis. And if we are rotating about the y-axis, we need to be in terms of y. Now, taking a look at this example, we want to find the volume of the solid obtained by rotating the region bounded by y equals the natural log of x, which looks like this. Y equals 1 and y equals 2. About the y-axis. So as I just said, if we're going around the y-axis, we need our integral to be in terms of y. So we are actually looking for this integral c to d of pi of whatever the function in terms of y is squared dy. Now y equals natural log of x, pretty easy function to solve. That is e to the y is x. So here is our function g of y being e to the y. Since we're going around the y-axis, our bounds are actually this 1 to 2. So our integral is pi of 1 to 2 e to the y squared dy, or pi integral 1 to 2 e to the 2y dy. Now, a quick u sub says that if we make u equal 2y and du equal to 2 dy, or 1/2 du dy, this integral becomes pi over 2 integral of e to the u du. And we plug in y equals 1 to get u equals 2. And when y equals 2, u equals 4. So our new bounds are 2 to 4. Now evaluating this, the integral of e to the u is e to the u. So we have pi over 2 times e to the u from 2 to 4, or pi over 2 times e to the 4th minus e squared. So that is the volume of this solid when we rotate around the y-axis. Now, for this next problem, everything stays the same. We're still using y equals the natural log of x, or we could say we're using x equals e to the y. We're still going from y equals 1 to y equals 2. But now, instead of rotating about the y-axis, we're rotating about the line x equals -2. That is over here. X equals -2. So when we rotate all the way around that axis, I want to move our graph over. And when we rotate about that axis, we're going to end up with a hole in the middle, because we're rotating about this line And so the reflection is that the y-axis gets reflected and our graph gets reflected over on this side. We're still going from y equals 1 to y equals 2. And our whole solid is now these big loops with a hole cut out in the middle. So if we cut through these solids, we get a cross section that looks like this outer function and an inner function. This sets us up for what is known as the washer method. Because now we have this hole, because we're going around this line x equals -2. There is our hole. And we have this small distance to just get to where we have some of our solid. And then we have the additional distance, that's the distance between our function and our smaller radius. So the washer method is the integral pi from a to b or c to d of the big radius squared minus the little radius squared. So now, taking a look at what these different circles represent, our center of our circle, because we're going around the x equals -2, that is line x equals -2. This first green circle is the y-axis that's going around. So from the line x equals -2 to the line x equals 1, that distance is 2. And then this farthest out circle still represents e to the y. And so going from x equals 0 to x equals e to the y, that distance is e to the y. So going from x equals -2 all the way out to e to the y, we get 2 plus e to the y. And so that distance is 2 plus e to the y, meaning our big radius is the 2 plus e to the y, and our little radius is just that 2. So we're looking at the integral of pi times 2 plus e to the y squared minus 2 squared dy. Our bounds are still from 1 to 2, just like before, but now this integral will calculate that solid that has that hole in the middle.